Trust me.
And sorry.
What? As he's recording. Yeah. Okay, so today we officially start talking about limits and have the actual notation for limits. So as a refresher from the last two lessons, so the tangent problem and the velocity problem, this is stated here towards the top. These we're trying to get you to understand the idea of a limit. So trying to show situations where one quantity was hard to find, either directly or precisely, so that would be the slope of the tangent line or that instantaneous velocity, but another quantity, if you calculate it repeatedly, so that would be your secant slopes or your average velocities, those hard to find values, the easy ones would approach the ones that were hard to find. So it's getting you that idea of the limit. And then I have those limits kind of written out into words, so not exact notation by any means. But for the tangent problem, so the limit as a point Q approaches point P on a curve, the limit of those secant slopes through P and Q would equal the tangent slope. And then for the velocity problem, the limit as I have T approaches T naught, so two values of time, but the limit of the average velocities between those two time values would approach the instantaneous velocity at time T naught. So getting that idea of a limit, and now we actually start to define it as more officially, I guess. I'll state it that way. So there are two ways to find or estimate the limit of a function, and that can be graphically or numerically with a table of values. So that's where we're starting with today, estimating limits using either tables or using a graph. And in this first example, this is already kind of set up for you just to give you the idea of what you're trying to do, and then we'll go through examples where we have to set this up. But it's starting out by saying investigate the behavior of the function f defined by f of x is x squared minus x plus 2 for values of x near 2. So near 2, that's an important way to phrase this. Actually, I'll highlight that. Because it only matters, and I'll discuss this a lot, it only matters in this case what's happening for the values of x near 2, but not equal to 2. So you'll hear me say, and you'll see with limits, that it doesn't matter what's actually happening at that specific value, but what's happening as you approach a value, or what's happening near that value if you get really close. So limits are all about that idea of closeness, what's happening as you approach a specific number, or part of a graph, or whatever it might be. We can investigate values, or investigate the function f for values of x both or near to both numerically and graphically. So I have a numerical table already set up for you. So this table will give values of f of x, or the y values for values of x close to 2 but not equal to 2. So there's that phrasing again, close to 2, but I do not have 2 actually part of this table at all. And how I have this table set up, it's kind of like where that middle part is. This is really two separate tables that we're looking at. So the first one, the one on the left, we're starting with the x value 1 and then using values of x that get closer and closer to 2. So these values are increasing. So these values are approaching 2. So we're approaching x equals 2. Specifically, I'm going to say from the left side, or from the left. So these are values that we are approaching 2, but they are less than 2. So they're from the left side of 2. And these are values that are less than 2, as I explained. So what's happening, or how this table is created, is these x values were actually substituted into the function. And that's where these y values are coming from. But as the x values approach 2, what would you say the y values are approaching? 4. So we can say as x, when you see that arrow, we'll learn with limits, as x is approaching 2, f of x is approaching 4. And then we can look at a similar idea, the right side of that table. So now I started with the x value 3, so a value that's bigger than 2. And these x values are getting smaller, but closer to 2. So I'll just put the note over here for these x values. So we are approaching x equals 2, but this time from the right side because their value is bigger than 2. And again, these were substituted into the function. That's where these y values are coming from. So now, as x is approaching 2, what would you say these y values are approaching? 4 again, yeah. So again, as x is approaching 2, the y values f of x are approaching 4. So with the limit, it is important, at least for today, we're going to be looking from both sides. So when you're approaching an x value, you should be approaching it from both sides, not just from the left or from the right side, but from both sides. And we can see from those tables that when x is close to 2 on either side of 2, the y value f of x is close to 4. So then if we were to look at this graphically, and you could make this graph on your graphing calculator or any graphing device, but I did include it on here, so the graph is given. From the graph, what we're looking for is as you approach 2 on the x-axis, you then look at, this is not the straightest vertical line there, but you then look at the curve to see, okay, from the left side of 2, as x is approaching 2, what is the y value approaching on the curve? As x is approaching 2 from values greater than 2, so on the right side, my curve would be here. What is it approaching? And in this case, we can see that it is approaching that y value of 4 also. The y values are getting closer to 4. So the way this is expressed, we say the limit of the function f of x equals x squared plus or minus x plus 2 as x approaches 2 is equal to 4. And this is the actual notation for it written as a limit. So the limit as x approaches 2 of x squared minus x plus 2 is equal to 4. Now, it just so happens for this particular function, if you just substituted 2 into the function value is 4. But again, it wouldn't have to be. It doesn't matter what's actually happening at 2. It's just what's happening when you get close to 2 on either side. So this y value for the function could be something totally different. It happens to be 4 for this one, but it doesn't have to be. So you're not just finding a function value. A limit is different. So on the reverse side here, how a limit is defined. So we write the limit as x approaches a of f of x is equal to L. So this is the notation for it. I have in words how to say that. So I know this says the limit of f of x as x approaches a. Whatever order you phrase that in doesn't matter. I usually say the limit as x approaches a of f of x. But that's how you would phrase it. That's how you would write it out in notation. And this is true if we can make the values of f of x arbitrarily close to L, so as close to L as we like, by taking x to be sufficiently close to a on either side of a, but not equal to a. So I include the definitions as they're given formally, although I think some other definitions are very wordy. So ultimately, it's just saying, again, as you take x values to be close to whatever a is on either side, but again, not equal to a. We don't care what is happening at a, just as you get close. You're looking for what's happening with the y values. What are they getting close to? So another way to phrase it, underneath there it says, the values of f of x become closer and closer to the number L as x approaches the number a from either side of a, but when x is not equal to a. So that's, I guess, a more friendly way to say what was above. Their definitions can get kind of wordy. And this is alternative notation as well, which shows f of x, or your y values approach L as your x values approach A. So this idea that we've talked about again, in the definition of a limit, f of x does not need to be defined when x equals A. So the only thing that matters is how f is defined near A. And these three graphs explain that idea a little bit better. So it says in each of these graphs, regardless of what's happening at the value A, they all have the same limit as x approaches A, and that limit is the y value L. So to help explain this a little bit more, the first graph, at the value A, the function is actually defined. So in this first graph, I'll say f of A actually equals L. So the function value at A is the y value L, and the limit as x approaches A is equal to L. In the next graph, notice there's a hole in the graph here, meaning this here, and I know it, whenever I copy this, it doesn't show up the greatest. This is your actual f of A right here.
So that's supposed to be filled in?
Yeah, this one is supposed to be filled in. The one on the curve should be a hole, not filled in. So that means this is your function value at A, and there's a hole in the graph. However, with a limit, this point doesn't even matter. As the x values approach A, on the curve, the y values are still approaching L. Even though the y value is never equal to L, it still approaches it. So that's why this is saying this limit is the same as this one, even though the function values at A are different. And then in this graph, so this again is a hole, and notice f of A doesn't even exist. So f of A for graph C is not defined. There's no point at A. There's no dot, if you will. So there's just a hole in the graph there, but again, the limit, as x is approaching A, the graph still approaches that y value L. So that's just trying to give you the idea that, again, at A, it doesn't matter what's happening. You can have a function value. The function value can be the same as the limit, but in all three cases, the limit is still that value of L. So that's what it looks like graphically. So I just have one example for you today, and we're still sticking with this idea of limits and looking more at limits with graphs and everything when we come back on Tuesday. But in this one example, it says to find the limit as x approaches 0 of the function sine of x over x. So we are going to find this limit numerically, and then I am going to look at the graph of it as well, but you're finding limits today numerically, so you're making those tables like was given to you here. Now, do you have to include as many values? No. I'll show you kind of the values I include. This is a lot. This is probably overkill. You don't need that many. And this is where the graphing calculator can come in handy and save you a lot of time. So one thing I want to point out first of all, say this is our function f of x, sine of x over x. My question is, our a value in this case is 0. We're approaching 0. Does f of 0, I'll say, exist, or is f of 0 defined for this function? Can x be 0 for that function? No, because we'd have a denominator of 0. So the answer to this is no. So just make that note that we can't just plug in 0 to the function, but that doesn't matter for the limit anyway. I'm just making that point because in the first example, we could have just substituted in the value. So I'm going to make one table where we are approaching x equals 0 from the left. So I'll make a table there, and then I'm going to make a separate table where we approach x equals 0 from the right. Because we want to approach x equals 0 on both sides. So from the left, so these would be values that are less than 0. So I could start out with, well, I could start out maybe with -1. I'm going to start out a little bit closer to 0, so I could do -0.5 and then get a little bit closer. I typically, these are the typical 4 I do, -0.5, and then I go to 1/10 of a unit away, so -0.1 in this case, and then 100th of a unit away, so -0.01, and then 1,000th away. So kind of thinking too, when we were choosing values of Q or choosing time intervals for average velocities, kind of those same distances apart. And then from the right side, because I can fill in these x values right away because I'll find all of my y values at the same time. So now values from the right would be values greater than 0. And again, I want to be half a distance away, 1/10, 100th, 1,000th. So in this case, it'd be +0.5, just the positive of all these values, +0.1, 0.01, 0.001. And I want to substitute these values into the function and find what their y values are, and then see as the x values approach 0 on either side, what do the y values approach. So as a reminder for you on your calculator, you can do this more quickly. Go to your y equals if you've forgotten about this. I think I showed it before. I'm going to clear what I have in mind. So if you have anything in yours, you might want to clear it. Ooh, also, one note, because we have a trig function, make sure you're in radian mode or you will not get the right values. So if you're not sure, if you are in other classes where you have to change to degree mode, mode is next to second. Just make sure that radian is highlighted and not degree. Or as you're following along with us, if you're not getting the same values, you're probably in the wrong mode. Yep. In mode, so yeah, it's right next to second. Make sure that radian is highlighted. Oh, did you see how to get there? Okay. All right, now I'm going to go back to y equals. So I'm going to type in my function, so sine of x, whoops, I did not hit the right value. Sine of x divided by x. And then make sure, just double check on your calculators, especially because I know some of you are borrowing the school one, so make sure this is already set up. But above Windows, if you hit second, you see TBL set, so that's table setup if you do second window. And just make sure, it doesn't matter what table start and the change in table are, but make sure where it says independent, ask is highlighted, and then dependent auto should be highlighted. And then you want to go to the table, which is second graph. And if you have any values already in here from using this before, to get rid of them, you have to individually delete each one. You have to hit the delete key and not the clear key. So delete is the third key along, not the main keys on top, the other top row. We have to hit delete for each one to get rid of them. You can just type over them too. And now I can type in all of my x values at once, and it'll calculate all of those y values. So I can type in -0.5, hit enter, -0.1, -0.01, -0.001, and then also the positives of those numbers, so +0.5, 0.1, 0.01, 0.001. And then just mark these values down. Remember too, you can arrow over, and if you highlight the values, it'll give you more decimal places. So I'm going to write down, I would write down more than 3 decimal places, maybe 5 or 6 in this case, because these values are going to be really close together, so you want those decimal places written down. So negative 0.5 is about 0.958851. I'll go to 6 decimal places. Negative 0.1 is 0.998334. Negative 0.01, 0.999983. And see, this is what I mean. Notice in your table, this shows up as 1, but if you highlight it, it's not really 1. It's just being rounded to 1, so don't just write 1 there. 0.999999, and you have to go farther than 683. Okay, and then I believe for the positive values, the y values are the same. Yes. So I'm just going to copy those down. Okay, so in looking at your 2 tables, from either side, as your x values approach 0, your y values are approaching what? 1. So we would then say that the limit as x approaches 0 of sine of x over x, this limit is equal to 1. And again, just make a note, the limit exists, the limit is 1. The function value, remember, doesn't exist, and that doesn't matter when it comes to the limit.
So, would you put all data goes
Yes, you can, yeah. Just as, yeah, to save yourself time. Oh, no, that's fine. Yeah, I put them all in the same one. And then I just copied them all down. So I entered them all right away. Couple of notes for you. So if you are asked to find or estimate a limit numerically, that's what this process is. This is what you need to show. So just like I said for finding slopes of secant lines and then finding the average velocities to then approximate slope of tangent line or slope or instantaneous velocity, do not just plug in a value that's super, super close and say, oh, that's about 1, so that must be the limit. To show a limit, you have to show the values are actually approaching that number. Because it's possible a limit will not exist. So just keep that in mind. This is what I would expect you to show if I asked you to find a limit numerically. Because we are going to have other ways to find them, so I'm just specifying the numerically part. If you, just quickly, if you graphed this, so it's already entered into your y1, because this involves trig, I may have talked about this before. Remember, there is a very nice trig viewing window. If you go to zoom and then number 7 is z trig. So just if you were to look at this graph, and I'm not sure if mine is showing there's a hole. It shouldn't actually be connected there. I'd have to zoom in. But you can check too the way, if I go to window now, it'll show me how it's scaled. So I think it is going by like every pi halves, I believe. But the y-axis goes from -4 to 4 and is counted by 1s. So this at least allows you to see on the graph, if x is approaching 0, the y values do appear to be approaching 1. And you could zoom in. I'm actually curious if, I'm going to move this up a little bit. if my graph shows there's actually a hole there. I'm not really sure.
Well,
No.
it's just saying like side. Like if you
Yeah. Right. But if you, I'm wondering if you did,
if you trace it, it doesn't give you a value.
yeah, if you trace it, oh, that's just the, I want this. Oh yeah, so if x is 0, it doesn't give you a y value because there isn't one. So you have to actually hit trace. I was just moving my cursor before. So, oopsies.